So as we go through this one, you've got your list plus or minus 1, 5 over 1, and 3, which basically means you have 1, 5, 1/3, 5/3, plus or minus, for your possible zeros. Okay. Yeah, 1 and 3 are the factors of 3. 1 and 5 are the factors of 5. Yep. Remember, this is the factors of the tail divided by the factors of the numerator. Those are all your possibles. So that's why you might have missed one. So as you go through, you start at 1. Nope. The -1. Nope. Try 5. That's going to be a big no, isn't it? That's not going to work either. So at this point, you're probably like, uh-oh. Try a third. What's a third of 3? 1. Okay. We add those. You add those together, you get -7. Now, if you do a third of that, it's -7/3, and it just seems to fall off the rail here. Watch what happens if you throw a negative from this. Doesn't that become -1 then? Isn't that -9? What's a third of -9? So we go there. Now we're back to El Poopsville. Okay. All right. What? Okay. Now, did you know there was another way to guess where to start? What is it? Yep. Surprised you guys didn't even think of that. You have this fancy. It's very, very rare that you get. And I know you're saying no calculator, right? There's times for calculator, non-calculator, and this is kind of one of those things. But if I throw non-calculator at you for something like this, it's something searchable, something findable. So let's see what we can find. No, I don't care about that. Let's see. Y equals. What were you ready to make it? Was it 3x squared or 3x to the 4th? Plus 16. Thank you, ma'am. Change my window around here so I can see it a little better. So it looks like 1/3 should have worked, doesn't it? If I'm looking at it, gee, wonder which one I would try. 0. Table would get you if you found an integer value, but then you have to look to see where it's crossing over. You could do a search value through it, but this is just as fast. Like 3/8. That's not one of my possibles, is it? Okay. It's weird. So let's see if the other one is then. Did I type that in correctly? Okay. So then let's see here. So we know if we went through 1/3. See, then you got, just for fun here, it'd be 2/3, and that won't get us there because we multiply that. 2/3, 16/3 would be what? 16 times 3 is 48, I believe. So 48, 48 thirds plus 2/3 is 50 thirds. 50 thirds times 1/3, negative 1/3 won't get us to -5, so that won't work. Then we have 5/3 left to check. So we try 5/3. 5/3 of 3 is 5. 5/3 of -3 is -5. So then now that becomes -50 thirds. But this is the same thing as 48 thirds, so that's -2 thirds. And then that's what? -10 ninths. That doesn't get you to 0. We try that with the negative. It's at -11. That's 15, isn't it? So that'd be 40 thirds. Yeah. What the big book of answers? Really? I guess what I wrote in my notes, you don't have my book. Guess who didn't look at their book before they assigned it? Yeah, don't worry about 54. It makes no sense. Yep. Anywho, let's not worry about 54. It never existed. What was the other one you wanted to look at? What do you got, Bill? 43? Sorry about that. I had no idea. Yeah, it's sitting right here. Skip. Don't ever do that. So mental note. You know what I should do? In my shell of my notes where I start, I'm gonna say skip 54 right at the beginning so I don't forget that again. So you have what? 1, 2, 3, 6, 9, 12. So we have 1, 2, 3, 6, not 9. 6, that'd be what? 12, 18, 36. Those possibles? 4 and 9. Forgot 4 and 9. Sorry about that. So start going through. Get there? Just starting in the last little bit of 6, 6 here. So that didn't work. Let's check 2. Were you here this morning? Yeah, that's what I thought. Whoa! All right, so let's try 3. Why didn't you just tell me it worked at 3? Wait, 1, 3, 3, 4, 12. Yeah. Thank you. Why did you tell me? You guys are mean. Did you forget the placeholder too, Bill? There we go. So now I'm at a fourth degree polynomial. And this is where, since we know that 3 is a 0, we have a term now of x minus 3. What you always want to do here, since you're at fourth degree now, is check 3 again. We know that 1 and 2, positive and negative, don't work. Because if those would have worked, we would have already been able to find a 0. So what we do is we check 3 one more time to see if, in fact, it has multiplicity. And obviously, it's not going to. So we know 3 does not have multiplicity. So then I go to the next number, which was negative 3. Negative 3, 1, negative 3, 0, 0, 4, negative 12, 0. Good. So now I also have a 0 at negative 3. So I have x plus 3. Now I'm down to a third degree polynomial. And if I look at that third degree polynomial, I could probably tell that I can't group it because those GCFs for everything are all sorts of messed up. So I'm going to try one more time with the negative 3, see if I can still go with a multiplicity just in case. It's down a bit. And no. It's kind of satisfying when you know the answer is no. So now we're up to what, 4? Nope. Negative 2? How did we skip over negative 2 earlier? Thank you. You're right. Excuse me. So now we're at what times what? What times what's positive 2? You add together to get negative 1. Nothing, which means you have to use. Then you got to do the dance. Remember the yellow person face and their legs are just kind of going back and forth? We could replay it, but. So let's see, that's 1 minus 8, so it's a square root of negative 7. Does that sound right? Negative 7? So your last 0 would be 1 plus or minus I root 7 all over 2.
This is so cool.
I don't like your sarcasm. Yep. When you get down to a quadratic, ladies and gentlemen, when that's something you cannot factor, that's when we're going to go ahead and go right to quadratic formula because that makes our lives easier. Okay. Let's see. What else we got? So this is my polynomial. So it gives me plus or minus 1, 5 over 1 and 2. So we have 1, 5, 1 half, 5 halves. a plus or minus to look for. So we start, make sure I don't have any placeholders I have to worry about missing this time. It doesn't look like I have already placeholders. So we have what, 2, 3, -3, 3, -5. Excuse me. Go with 1. I highly recommend putting the smiley face at the end because it makes you feel good. I always like to go back and circle knowing that was a 0. If that's my 0, my term is x minus 1. And you guys can probably see right here, isn't this a great one for a grouping? You see right away. Look at your coefficients. So you have 2x cubed plus 5x squared plus 2x plus 5. So if I do GCFs, I have an x squared and I have a 2x plus 5. Take out a positive 1, I have a 2x plus 5. That gives me terms of x squared plus 1, 2x plus 5, which zeros then are at, we'll move these guys here, these are all of my terms. We have 1 plus or minus I and -5/2. When you have x squared plus 1 set it equal to 0, you subtract 1, take the square root. Whenever you take the square root over an equal sign, it's always plus minus. Always. Okay. Just like when we had x squared minus 4, it would be plus or minus 2. Same idea. What do you say we start a little bit of 6, 7? Make sure your name's on that one. Send that one up. Let's do a little bit of 6, 7. Yeah. You have lots and lots. Wait, how about this? Screw it. Hold on to it. You all got it. I'll give you all 10 points for it. Merry Christmas. This is too much paper. Too much paper. Because now it gets to be fun. So here's where it gets cool. Here's where it gets cool. Like, as in, it's like, it's why everything we've been doing works. It just works. Because Murphy said so.
Are we going to do proofs?
So we start going through this, the good old-fashioned fundamental theorem of algebra. As this gets going, this is why everything that we've been talking about works. This is why we've always said certain things. Nth degree. Who is it? Housekeeping? Hello, Lily. How are you? Did you want to come to class? Okay. So, as we were saying before, as we've gone through this over and over and over again, nth degree polynomials have how many possible zeros? Has n possible zeros. Do those zeros have to be real? No, not at all. So you might have noticed that a lot of times when you had even polynomials, even degree polynomials, they wound up with an imaginary solution set. It happens. When you have an nth degree polynomial, how many changes of direction will it have? N minus 1. You have n minus 1 changes of direction. And I want to keep remembering to say that it's possible. Because you could have a fourth degree polynomial that has no zeros, no real zeros, and only one change of direction? It's completely possible. Okay. So the idea is that these are the possible scenarios. If you have an nth degree polynomial, you have n number of zeros, you have n minus 1 changes of direction. And you guys were saying this a second ago, because I think I went on a sequence of what we said in class before. It would have n plus 1 terms in the polynomial. And we looked at it that way when we were dealing with synthetic substitution, synthetic division. We always make sure we have n plus 1. Now, excuse me. The idea of what they call the fundamental theorem of algebra is basically when you solve for x, you get an answer. You've been solving for x your whole life. You've been solving those quick variable things as long as I can. Having kids that have started in elementary school, I know when they start learning how to solve equations. You do a lot of that stuff back in kindergarten, first grade. You probably didn't ever even realize it. When you had this.
We just do this for the rest of the year.
How many apples do we need to put in the box to make it equal that many apples on the end? We had to put 3 more apples. Okay? SMRT. So when you did this stuff in kindergarten, which eventually became this stuff in first grade, you started to find the answer. How many possible answers are there to get that answer? To get that? There's only one, isn't there? What's the degree of that? It's a first degree polynomial, isn't it? It's a first degree polynomial. All right? It's a first degree polynomial. How many possible zeros can it have? 1. How many? Okay. Is it? All right. So what's your answer here? Okay. If x equals 4, you were just saying it's up and down, isn't it? That's a vertical line, right? Are there any changes in direction with that? No. Where does it cross the x-axis? At 4. What's the answer? 4. You've been doing all of this forever. You just didn't realize that basically what happens with this fundamental theorem of algebra, it states that for any value of x over the complex nth degree of x over the complex numbers, real, imaginary, there is always n possible zeros. Always. If this was, remember when you had this? If you FOILed that out, you have x squared minus x minus 6. When you did that, you factored that. When you factored that, you had, it gave you zeros at -2 and 3. Where did it cross the x-axis? -2, 3. How many changes of direction did that have? 1. This is a square. Change direction. Where did it change direction? At its vertex. You guys have been doing this style of idea ever since you learned how to solve for x back in kindergarten, first grade. They've been slowly building you guys up to the idea of what the fundamental theorem of algebra means. Which way are your tails going in this one? Up, up. Okay. That's the other thing that we learned. We learned about degree. We learned if it's down, up. Is it up, up? Is it up, down? Is it down, down? There's only 4 possible ways it can work. There's always going to be only 4 possible ways that it works. That never changes. Okay? So what happens is we get into this. We did this one. So if we go through with an nth degree, if I want to go through all of this, I want to list tails. I want to plot my zeros on a graph. I'm sorry, let me rephrase it. I want to list my terms. I want to put my zeros. I'm going to plot my zeros, and I'm going to graph it with my tails. This is kind of where everything we've done kind of builds to a head. Okay? This is where we've gone through, we've done all of this work. So if we have x to the 4th plus 4x cubed minus 6x squared minus 36x minus 27, what's the degree of that polynomial? 4th degree polynomial. How many terms should be in the polynomial? 5. Do we have all 5? Okay. How many possible zeros can we get? 4. How many changes of direction can we have? 3. What are your tails doing? Up, up. See where I'm going with this? You know how to set up every single dip here. Where do you do what do you do to start searching for zeros? Synthetic division. What are your possible zeros? Okay. And then you just start fishing. Okay. You just start fishing for it. You just start looking. 1, 4, -6, -36, and 27. Thank you. I found a 0. I have a 0 now at -1. If -1 is my 0, I have a term of x plus 1. When I look at that polynomial now, it's now a 3rd degree. But if you look at the coefficients, doesn't that look like I can group it? When you start noticing things like that, you're like, I wonder if I can do that. Do you have to right away? No, if you're more comfortable just continuing on with your synthetic, get you down to a quadratic, go for it. Me, I see a 1 and a 3, a -9 and a -27. In my mind, that's telling me I can take out that -9. I can make it 2 terms of x with the 1 and 3s. So I'm going to group it. So I have x cubed, 3x squared, 9x, 27. I group here. And this part, when you have that negative x value, this is where most of you guys make your mistake. Remember, if it's negative on this term, bring the negative inside so that way you remember to take it out. That's where a lot of you guys make a mistake. Okay? So you have x squared, x plus 3. Take out the -9, and you have x plus 3. Are those 2 things in the parentheses the same thing? That's a very good sign. So you have x plus 3, x squared minus 9, along with this guy. That gives me all of my possible zeros. I have zeros now at -1, -3, and plus or minus 3 again. Which therefore means, where does the multiplicity occur? At -3. The multiplicity occurs at -3 because it's repeated, which means what happens graphically? It changes direction at the multiplicity. So there's multiplicity at -3, multiplicity of 2 at -3. So graphically, oops, sorry, I'm going to go too far down. Our tails were up, up, correct? Okay. We have zeros at -1, -3, +3. In our original polynomial, there's another value here, oops, that you know without thinking too hard. What other thing can I graph without having to think too hard? What is it? Y-intercept. Where's your y-intercept on this? -27. Yeah, that constant. If x is 0, you have y-intercept. So you know somewhere down here, let's here right now. We'll just say that's -27. I know that's going to occur. It doesn't have to be scaled perfectly, but I know it happens. So I get the idea of how far down it's going to go back up through. So we have multiplicity at -3. So it tails up, changes direction, has to come back down, and tail up. It'll look something like that. Squinting is probably correct. Squint the other way, it might not be, but the idea is this is how we've been able to do everything. Bit and piece, just starting to chug along. Terms and parentheses generate zeros. Zeros are plottable. Yes, ma'am. Correct. Yep. Because wherever there's multiplicity, it means it changes. If it's an even multiplicity, it changes direction at that 0. If it's an odd multiplicity, it goes through the 0. Okay? That's the difference. All right?
So it doesn't change direction.
No, it goes through.
Okay.
Yeah. It's if this had multiplicity of 3 at -3, it would have gone through this, and then it would change. It would have been a little bit different. Okay. Pretty good. All right. So what we're going to be able to do today, guys, is we'll be able to take. Oops. Whoa. We'll be able to take something like this and do the whole deal. This one's really easy. Because what can you do right away with this? Factor how it says, yeah. What times what's -12? You add together -12, you add together to get +1. -3 and +4, right? Okay. So you have x squared plus 4, x squared minus 3. Where are your zeros? Plus or minus 2i, very good. Plus or minus √3. How do we graph imaginary? Just use your imagination. I am right now. There is a way to plot imaginary numbers, but when you graph them with polynomial stuff, it doesn't work as clean as you'd like it to. So here's what happens. Let me show you what it looks like. It was what? X to the 4th plus x squared, and then minus 12. Okay. I gotta change my window back here. We go to -15 by 15. Because we know that we have a y-intercept at 12, right? So when you look at it, it's just going to do that. What happens there is that you're only going to be able to plot the 0 that's real. There will be times, if you look at graphs on the calculator, if there are imaginary zeros, they might do that little change of direction above or below the axis. That could happen. That's when you have to have a calculator to make sure you know what's going on. But the idea here is you still got that. Right? Excuse me. All right. So yeah, fundamental theorem of algebra is If f, don't write this down. If f of x is a polynomial of degree n where n is greater than 0, then the equation f of x equals 0 has at least one root in the set of complex numbers. For every n degree, there's n 0. This is why when you solve for x, you got an answer. That's why it works. This is why math maths. We still have time here. Let's do this one. Let's do this one. Let's find all of our zeros, and let's plot it via zeros and tails. Let's see what we can do. Now, at this point, you guys kind of have a whole bunch of stuff at your disposal to decide how you want to factor. Doesn't matter which way you do it. Nope. Not at all. Not at all. Now, I'm thinking that this is one of those really good examples to group. Did you guys group?
Yeah.
Good. When you group, you get x squared, x plus 3, that's 16, x plus 3. And then this is -3. Now, I think this is one graph that has that dip above the axis. Throw that in your calculator real quick. Did you know that you could throw it in the calculator like this with the terms? Yeah, it does the same thing. Sometimes it's quicker to type that than it is all the other stuff. So let's see. I hit the right button. Yeah, if you hit the right buttons. I think this is the one that actually. No. Never mind. You might have to search the window. I thought it did. See. Anyway, we did the. I put it in as that, which is the same thing. Because you should be down up, because the tails are. And it was down up. We had the 0 that went through -3. My graph was. I changed my windows just so I can show the graphs. My windows can be all sorts of messed up. So what I want to try tonight, I think I have to adjust the PDF file. In 6-7, I want to do 27 through 33 all. And I want you guys to get zeros and plot via tails. Okay? If you do come across imaginary zeros, which you will, plot your tails like you think they would be, and don't forget to throw in like your y-intercept. Plot your tails like you think it's going to look. Look at your graphic calculator real quick to see if there is a little dip above or below. Sometimes that happens. But don't rely completely upon the graphic calculator. Yes, sir.
So when you say find it via scale, you're writing down the tail.
No, when you graph it. So you're going to plot your zeros, and then you would do your change in direction and do the tail graph. So if you had zeros, just like we did a minute ago, remember how we had zeros? We had that -3, -1, and a 3. We did this, or whatever it looked like. That it would look something like that. That's what I mean by graphic. We'll go from there. Yeah, I'll be right there. Let me pull this up.